Hello everybody! Now you've made to the final day, or day 10, of our crash course. Congratulations! In this session, we're going to try to predict what's going to happen with LLM and AI. For more AI courses and interview materials, please go to bowsy8.com. AI's rapid progression in recent years is nothing short of transformative. LLMs have emerged as the leading technology in the AI field, revolutionizing areas like natural language processing, machine translation, and content creation. These models have moved beyond basic text generation, evolving to provide meaningful insights, generate human-like dialogue, and even contribute to decision-making processes in various industries. However, as powerful as these tools are, the future of AI is not without its challenges. The integration of LLMs into everyday life raises important questions about privacy, bias, and accountability. As we explore the future of LLMs, we must address both the immense opportunities and the complex issues that accompany their widespread adoption. The development of LLMs has undergone a major transformation, from early rule-based systems to modern neural networks. Rule-based models relied on handcrafted rules and logic to process language, but they struggled with generalization and scalability. With the advent of deep learning and neural networks, the field shifted towards models that could learn directly from vast amounts of data. The introduction of the transformer architecture in 2017 was a pivotal moment, as it enabled better handling of long-range dependencies in sequences and significantly boosted the efficiency of LLMs. Building on this, models like GPT-4 and other variants have continued to refine and expand on these techniques, scaling up the number of parameters and improving the model's capabilities. Looking ahead, we expect to see further improvements in LLM architecture, including hybrid models that combine different learning paradigms, enhanced attention mechanisms for more contextual understanding. Self-supervised learning has emerged as a key methodology in training LLMs, helping them learn from large amounts of unlabeled data. Traditional machine learning techniques, particularly supervised learning, require vast amounts of labeled data, which is often expensive or impractical to collect. Self-supervised learning addresses this challenge by creating labels from the data itself, allowing LLMs to train on enormous corpora of text without the need for manual annotation. One common technique is predicting missing words in a sentence or predicting the next word in a sequence, which allows the model to learn underlying language patterns and contextual relationships. This approach has been instrumental in developing powerful LLMs, which was trained on massive datasets of text with minimal human supervision. As the field continues to evolve, we can expect more advanced self-supervised techniques that will further enhance the capabilities of LLMs, making them more effective in low-resource environments and more adaptable across domains. Federated learning is an innovative approach to machine learning that allows models to be trained across decentralized networks, maintaining data privacy by keeping the data localized on individual devices. In traditional machine learning, large datasets are collected and stored in a central location for model training. However, this poses privacy risks, particularly in fields like healthcare, where sensitive personal data is involved. Federated learning solves this by training models directly on user devices and only sharing model updates, rather than raw data, with the central server. This approach not only enhances privacy, but also reduces the need for transferring vast amounts of data, which can be costly and time-consuming. For LLMs, federated learning presents an opportunity to improve performance while ensuring data privacy and security. It also has the potential to scale to millions or even billions of devices, creating more robust and adaptable AI systems. Transfer learning is one of the most effective techniques used to improve the performance of LLMs. Instead of training a model from scratch for every new task, transfer learning allows models to leverage knowledge from previously learned tasks. This strategy significantly reduces the time and data required for training in new domains, making it possible to apply LLMs to a wide variety of tasks with minimal additional training. For example, a model trained on general language understanding can be fine-tuned for specific applications like legal document analysis or medical text classification, enabling it to perform these tasks with much greater accuracy. Transfer learning facilitates cross-domain knowledge sharing, allowing models to adapt to new domains quickly and efficiently. In the future, we expect to see even more sophisticated transfer learning methods that enable LLMs to transfer knowledge not just across tasks, but also across modalities, such as combining text, images, and audio. Knowledge graphs have become an essential tool for enhancing the performance of LLMs by providing structured representations of knowledge. These graphs capture relationships between entities in a visual, graph-based format, which allows models to better understand the context and semantic connections between words or concepts. When incorporated into LLMs, knowledge graphs enable more sophisticated reasoning, question answering, and the generation of responses that are grounded in real-world knowledge. For example, a knowledge graph might help an LLM better understand the relationship between medical terms, enabling it to provide more accurate diagnoses or suggest treatments. In the future, we anticipate a more seamless integration of dynamic knowledge graphs into LLMs, where models not only learn from static knowledge, but can also access real-time data and continuously update their understanding of the world. This integration could result in LLMs that are more adaptive, contextually aware, and able to provide up-to-date information across a wide range of fields. AI agents are evolving beyond simple response generators into autonomous decision makers capable of reasoning and adapting to new situations. These agents leverage reinforcement learning to optimize their actions based on trial and error feedback, enabling them to make complex decisions in dynamic environments. For example, AI-driven financial advisors can analyze market trends and suggest optimal investment strategies, while robotic process automation (RPA) systems can autonomously streamline business operations. However, with increased autonomy comes greater ethical concerns. Who is responsible when an AI agent makes an incorrect or harmful decision? How do we ensure fairness and accountability in AI-driven decision-making? These questions will become more critical as AI agents integrate into industries such as healthcare, cybersecurity, and autonomous vehicles. Looking ahead, future AI agents will likely incorporate a mix of symbolic reasoning, deep learning, and human-in-the-loop approaches to enhance their decision-making capabilities while maintaining transparency and control. The challenge will be to balance autonomy with oversight, ensuring that AI remains beneficial and aligned with human values. LLMs are reshaping human-AI collaboration by serving as intelligent assistants that enhance productivity across various domains. AI-assisted workflows are becoming increasingly common, with LLMs generating reports, drafting legal documents, and even assisting in scientific research. Tools like GitHub Copilot demonstrate AI's ability to accelerate software development by suggesting code snippets in real time. However, challenges remain, particularly in ensuring seamless and effective human-AI communication. Misinterpretations, biases, and the limitations of AI-generated outputs can hinder collaboration. The future will likely see more refined AI copilots that integrate multimodal inputs, allowing for richer interactions beyond text. These systems will evolve to better understand user intent, provide contextual insights, and work alongside humans in a way that feels more natural and intuitive. As AI continues to integrate into the workplace, the focus will shift toward developing interfaces and interaction paradigms that maximize efficiency while maintaining human oversight and creativity. Personalized AI is becoming a key trend, with users demanding more tailored interactions from LLMs. Companies are developing AI models that adapt to individual preferences, learning from user behavior to provide more relevant responses. Personalized AI assistants can enhance productivity by automating tasks and anticipating user needs. However, customization raises privacy concerns as more user data is needed to refine these models. Techniques like federated learning and on-device AI processing can help mitigate risks by keeping data local. The future of personalized AI will likely focus on balancing adaptability with privacy, allowing users to benefit from customized experiences without sacrificing security. AI-generated content is transforming creative industries. Tools like DALL-E and ChatGPT enable the rapid production of art, music, and literature. AI assists human creators by generating ideas, refining drafts, and automating tedious tasks. However, concerns around originality and copyright remain, as AI models are trained on existing content. Future advancements will likely focus on more interactive AI-human collaboration, where AI serves as a creative partner rather than a mere tool. Ethical and legal frameworks will also need to evolve to address ownership rights in AI-generated works. The foundational architectures behind LLMs are evolving rapidly. While transformer-based models like GPT have been dominant, future models may incorporate entirely new architectures designed for greater efficiency, interpretability, and reasoning capabilities. Hybrid AI models are emerging, combining deep learning with symbolic reasoning, which can improve explainability and enhance logical reasoning. For example, integrating knowledge graphs with neural networks could allow models to retrieve factual information more accurately rather than relying solely on statistical correlations from training data. Another significant trend is modular AI architectures, where different components of a model specialize in particular tasks. Instead of training a single massive model, modular approaches allow for more efficient scaling by distributing processing across multiple specialized subsystems. This could lead to models that adapt dynamically to different tasks, improving efficiency and reducing computational costs. However, these advances come with challenges. Training new architectures at scale requires enormous computational resources, and ensuring stability across hybrid or modular models remains a technical hurdle. Future research will likely focus on optimizing these architectures for speed, energy efficiency, and adaptability while maintaining high levels of accuracy and generalization. Currently, most LLMs operate as static models, trained once on large datasets and then deployed without ongoing updates. However, the future of AI lies in self-improving models capable of learning and adapting post-deployment. On-device learning will allow models to personalize responses based on user interactions while preserving privacy through techniques like federated learning. This could lead to AI assistants that evolve to match individual user preferences without requiring centralized retraining. Continual learning, where models update incrementally over time, presents a significant shift from traditional training paradigms. Instead of requiring periodic retraining on massive datasets, AI systems will need to integrate new knowledge dynamically while avoiding catastrophic forgetting, where new learning overwrites previous knowledge. However, challenges such as data drift, where incoming data gradually shifts from the training distribution, must be addressed to maintain model reliability. Future research will focus on developing mechanisms for stable, adaptive learning that balance efficiency, memory retention, and ethical considerations. If successful, self-improving AI could lead to systems that remain relevant and useful without frequent manual interventions. AI models, especially LLMs, demand immense computational power, leading to high energy consumption and environmental concerns. Training state-of-the-art models requires thousands of GPUs, consuming vast amounts of electricity. The future of AI will focus on optimizing efficiency through better training algorithms, hardware acceleration, and model compression. Techniques like knowledge distillation, pruning, and quantization allow for smaller, faster models that retain high performance. Additionally, hardware innovations such as AI-specific chips, e.g., TPUs and neuromorphic processors, will further reduce computational costs. The long-term goal is to develop LLMs that operate efficiently on consumer devices, minimizing reliance on cloud-based supercomputers while maintaining performance. Future AI systems will be inherently multimodal, processing and understanding multiple data types, including text, images, video, and audio. Current LLMs are primarily text-based, but integrating multiple modalities enhances comprehension and reasoning. For example, models trained on both images and text can better understand visual scenes and context. Cross-modal learning also allows AI to generate richer, more context-aware responses. However, challenges exist in aligning different data sources and ensuring smooth interactions across modalities. Future advancements will likely improve how AI fuses and interprets diverse data, leading to more natural, intuitive AI experiences, such as seamless human-AI collaboration in real-time multimodal environments. While large, general-purpose models have been dominant, there is a growing shift towards smaller, task-specific models that are optimized for particular domains. Fine-tuning pre-trained LLMs for specific tasks allows for more efficient deployment with significantly reduced computational demands. These smaller models can often outperform larger counterparts in narrow applications because they are trained on highly relevant data. Additionally, task-specific models can run on edge devices, reducing dependency on cloud infrastructure. This trend aligns with the need for more accessible, energy-efficient AI solutions. Moving forward, AI development will likely involve a combination of large foundation models for general knowledge and smaller, customized models for specialized applications, striking a balance between adaptability and efficiency. A major shift in AI research is the development of self-improving models, AI systems capable of continuously learning and refining themselves without human intervention. Instead of requiring frequent retraining on manually curated datasets, future LLMs may autonomously analyze new data, adapt their internal representations, and improve their responses over time. However, unsupervised self-learning presents significant risks. Without proper safeguards, models could drift away from reliable outputs or reinforce biases present in newly encountered data. Stability is also a concern. Frequent updates could lead to inconsistencies or even degradation in model performance. To address this, researchers are exploring hybrid approaches where models autonomously learn but are periodically assessed and corrected through human oversight or auxiliary AI systems designed to monitor quality. In the long run, self-improving AI could drastically reduce the costs of model maintenance and enable LLMs that remain perpetually up to date with the latest knowledge and linguistic trends. Currently, most LLMs operate as static models, trained once on large datasets and then deployed without ongoing updates. However, the future of AI lies in self-improving models capable of learning and adapting post-deployment. On-device learning will allow models to personalize responses based on user interactions while preserving privacy through techniques like federated learning. This could lead to AI assistants that evolve to match individual user preferences without requiring centralized retraining. Continual learning, where models update incrementally over time, presents a significant shift from traditional training paradigms. Instead of requiring periodic retraining on massive datasets, AI systems will need to integrate new knowledge dynamically while avoiding catastrophic forgetting. However, challenges such as data drift must be addressed to maintain model reliability. Future research will focus on developing mechanisms for stable, adaptive learning that balance efficiency, memory retention, and ethical considerations. Current LLMs, based on transformer architectures, have demonstrated remarkable capabilities, but they are reaching fundamental limits. One of the biggest challenges is scalability. Training models with trillions of parameters requires immense computational resources and energy consumption. Additionally, transformers suffer from inefficiencies, such as quadratic complexity in attention mechanisms, making them costly for long sequences. Beyond hardware limitations, another challenge is the diminishing returns of simply increasing model size. While larger models tend to perform better, gains become marginal, and issues like hallucination, bias, and factual inconsistency persist. Researchers are exploring alternative architectures, such as state-space models, retrieval-augmented generation, and neuromorphic computing, to overcome these bottlenecks. In the future, the field may shift towards more efficient AI paradigms that require less data and computation while maintaining high performance. Neuromorphic computing is an emerging field that seeks to design AI systems inspired by the brain's biological efficiency. Unlike traditional deep learning models that rely on vast amounts of matrix operations, neuromorphic chips and spiking neural networks, SNNs, process information asynchronously, consuming energy only when necessary. This makes them highly efficient compared to power-hungry GPUs and TPUs. Spiking networks also have the potential to handle time-dependent information more effectively, making them promising for next-generation AI applications requiring real-time adaptation. Despite their advantages, neuromorphic systems are still in early development, with challenges in hardware design, training methods, and integration with existing architectures. Future research aims to bridge the gap between neuromorphic computing and mainstream AI, potentially leading to models that are not only more efficient, but also biologically inspired in their processing and reasoning capabilities. The next frontier for LLMs is moving beyond text-based intelligence to true multimodal capabilities. Future AI systems will not only process text, but also integrate vision, audio, and sensor data to develop a richer understanding of the world. However, cross-modal learning introduces challenges. Different data types require specialized processing, and aligning them into a unified representation remains complex. Current approaches, such as OpenAI's GPT-4v and DeepMind's Gemini, are early steps toward generalist AI, but these models still struggle with reasoning across multiple modalities seamlessly. The ultimate goal is to create AI that can fluidly understand and generate across domains, leading to applications in robotics, augmented reality, and complex decision-making. Advancements in multimodal learning will drive AI closer to human-like general intelligence, enabling more natural interactions and deeper contextual understanding. Future AI systems will play a crucial role in knowledge synthesis, combining information from vast and diverse sources to generate new insights. LLMs are already proficient in summarizing documents, but next-generation AI will go beyond that, identifying connections between seemingly unrelated fields. This could lead to advancements in interdisciplinary research, where AI can analyze knowledge across mathematics, philosophy, and computing to propose novel theories. Additionally, AI will improve the efficiency of literature reviews and meta-analyses, ensuring that human researchers can focus on deeper conceptual work. However, knowledge synthesis is not just about gathering data, it requires critical thinking and contextual understanding. Current AI models struggle with assessing the reliability of sources and distinguishing between correlation and causation. Future developments will focus on refining AI's reasoning abilities, enabling it to contribute meaningfully to intellectual and theoretical discourse. A key limitation of current LLMs is their reliance on pattern recognition rather than true reasoning. While they can generate text that appears coherent, they often struggle with logical consistency, causal relationships, and abstract reasoning. Future AI research will focus on improving reasoning capabilities, blending traditional symbolic AI with modern deep learning techniques. Symbolic AI methods, which rely on explicit rules and logic, may help LLMs develop more structured problem-solving skills. Hybrid models that integrate neural networks with reasoning engines could lead to AI systems capable of making deductions, verifying arguments, and even proposing solutions to unsolved problems. However, challenges remain, such as defining robust reasoning frameworks that are interpretable and scalable. As AI reasoning improves, it could enhance applications in automated theorem proving, decision-making, and strategic planning. As AI systems become more sophisticated, understanding how they arrive at their conclusions is critical. Current LLMs function largely as black boxes, providing answers without clear justifications. This lack of transparency is a major issue for trust, accountability, and ethical deployment. Explainability techniques such as attention visualization, feature attribution, and rule extraction aim to make AI more interpretable. However, as models grow in complexity, maintaining transparency becomes increasingly difficult. There is an inherent trade-off between accuracy and interpretability. Highly complex models may outperform simpler ones, but at the cost of explainability. Future AI systems will need to integrate transparency at their core, possibly through modular architectures that allow for explicit reasoning steps. Explainable AI, XAI, will be essential for regulatory compliance, safety-critical applications, and user trust in AI-driven decision-making. AI ethics has evolved from basic concerns about fairness and privacy to a more nuanced framework that includes responsibility, accountability, and transparency in AI systems. As AI systems become more autonomous and integrated into society, new ethical challenges emerge, requiring innovative approaches to governance. Traditional ethical frameworks, such as deontology and utilitarianism, may need to be adapted to address unique concerns like algorithmic bias or decision-making in AI. This shift necessitates the development of AI-specific ethical guidelines, ideally shaped through interdisciplinary collaboration across fields such as computer science, philosophy, law, and sociology. The future of AI ethics involves a more nuanced understanding of moral responsibility in the context of increasingly complex AI systems. AI has historically been designed for specific tasks, narrow AI, such as language translation, image recognition, or game playing. However, the dream of artificial general intelligence, AGI, seeks to create machines capable of understanding and performing any intellectual task that a human can do. Developing AGI presents a range of challenges, including creating models that can generalize across diverse domains and tasks. AGI could bring immense benefits, such as improving global problem-solving capabilities, advancing research, and facilitating innovation across multiple sectors. However, its development raises serious ethical concerns regarding control, safety, and societal impact. As AGI approaches, it will be essential to ensure proper governance and safety measures. Human-AI collaboration is an exciting area where AI tools are used to augment human cognitive abilities, enhancing decision-making, creativity, and problem-solving. For instance, AI can assist in data analysis, helping individuals make better-informed decisions in areas like business, healthcare, and research. Cognitive augmentation could empower individuals by providing personalized learning experiences or optimizing mental workloads. However, challenges remain in human-AI interaction, such as ensuring that AI complements rather than overrides human judgment. Moreover, the ethical implications of cognitive enhancement need to be carefully considered, especially regarding equitable access and the potential for misuse in competitive fields or military contexts. AI systems, while powerful, are susceptible to vulnerabilities, especially to adversarial attacks where small, imperceptible changes in input data can significantly affect AI performance. These vulnerabilities raise concerns in high-stakes applications such as autonomous driving, healthcare, and finance. Identifying and mitigating these risks is essential to building robust AI systems that can withstand intentional attacks and unexpected data inputs. Research into adversarial machine learning has led to techniques for improving model robustness, such as adversarial training and model regularization. In the future, AI security will become a critical focus, with efforts aimed at making AI systems not only more accurate, but also more secure and resilient to various threats. AI is reshaping the workplace, from automating routine tasks to augmenting human capabilities in various sectors. In industries such as manufacturing, logistics, and customer service, AI-driven automation is expected to replace certain jobs, leading to displacement in some sectors. However, AI also creates new opportunities in fields like AI development, data analysis, and robotics. The key challenge is ensuring that workers can adapt to this shift by reskilling and upskilling. Educational systems and businesses must prioritize lifelong learning programs to help the workforce navigate the challenges of an AI-driven economy. Additionally, a balanced approach is needed to ensure that the benefits of AI are shared equitably across society. Neuromorphic computing is an emerging field that seeks to design computing systems inspired by the human brain's neural architecture. Unlike traditional AI architectures, which rely on conventional silicon-based processors and von Neumann computing models, neuromorphic computing utilizes brain-like circuits that mimic biological neurons and synapses. This approach enables more efficient and adaptive AI systems, particularly in energy efficiency and real-time learning. Neuromorphic chips, such as Intel's Loihi and IBM's True North, are designed to process information more like a human brain, potentially leading to faster, more efficient AI. The applications of neuromorphic computing span from robotics to edge AI, where power efficiency and real-time learning are crucial. For example, autonomous drones and prosthetics could benefit from neuromorphic AI, adapting to new environments with minimal computational overhead. However, significant challenges remain, including hardware scalability, programming complexity, and compatibility with existing AI software frameworks. As research in this field progresses, neuromorphic computing could redefine AI capabilities, paving the way for systems that learn and adapt dynamically with minimal data input. AI is increasingly being used to assist in creative problem solving across various fields, from product design to scientific research. Unlike traditional AI applications that focus on automation and prediction, AI-driven creativity involves generating new ideas, designs, and solutions that humans might not conceive. Advanced generative models, such as OpenAI's GPT and DeepMind's AlphaCode, help engineers and researchers tackle complex challenges by offering unique insights and innovative approaches. AI-powered brainstorming tools analyze vast amounts of data, recognize patterns, and suggest novel concepts. In industrial design, AI enhances ideation by generating multiple prototypes based on functional requirements and aesthetic preferences, significantly accelerating product development cycles. AI is also being used in pharmaceutical research to suggest new molecular structures for drug discovery, reducing the time required for experimentation. The future of AI-driven creative problem-solving will likely involve deeper human-AI collaboration, where AI acts as a co-creator rather than a mere assistant. However, challenges remain in ensuring AI-generated ideas align with ethical and human-centered design principles. As AI becomes more integrated into creative workflows, balancing machine-generated innovation with human intuition and oversight will be crucial to maintaining meaningful and impactful innovation. AI architectures have undergone significant evolution, moving from early rule-based systems to today's deep learning models. Initially, expert systems relied on predefined rules, limiting their scalability and adaptability. The rise of machine learning introduced statistical approaches, enabling models to learn patterns from data rather than relying on rigid rules. One of the most groundbreaking advancements in AI has been transformer-based architectures, such as OpenAI's GPT and Google's BERT. These models revolutionized natural language processing by leveraging self-attention mechanisms, allowing for more efficient, contextual understanding. Unlike previous recurrent architectures, transformers process entire sequences in parallel, making them more scalable for large-scale AI applications. Looking ahead, hybrid AI models that integrate different learning paradigms, such as combining symbolic AI with deep learning, are emerging as a promising approach. This fusion enables AI to incorporate reasoning capabilities while maintaining the flexibility of data-driven learning. Additionally, the future of AI model design will focus on efficiency improvements, including sparsity techniques, modular architectures, and dynamic adaptation to various computational environments. As AI scales, reliance on labeled data becomes a bottleneck, necessitating a shift towards self-supervised and unsupervised learning methods. Unlike supervised learning, which requires extensive human-labeled datasets, self-supervised learning, SSL, allows models to learn representations from raw, unlabeled data by leveraging intrinsic structures within the data itself. Self-supervised learning plays a crucial role in training large language models. Techniques such as masked language modeling, MLM, as used in BERT, involve predicting missing words within sentences, enabling the model to develop a deep understanding of context and semantics. Contrastive learning, another self-supervised approach, enhances representation learning by maximizing similarity between positive pairs, e.g., different views of the same data, while minimizing similarity to negative pairs. This method is instrumental in multimodal AI applications where text, image, and audio data need to be aligned meaningfully. Despite its advantages, unsupervised learning faces challenges, including difficulties in evaluating model performance and ensuring robustness against biases. Since these models learn from raw data without explicit human guidance, they may capture unintended correlations, leading to unpredictable behaviors. One limitation of current LLMs is their inability to retain long-term context efficiently. Future AI developments are exploring ways to integrate more advanced memory mechanisms, allowing models to recall information across extended conversations and interactions. Memory-augmented neural networks introduce external memory storage that enables AI models to retrieve past interactions efficiently. This approach mimics human-like memory recall, enhancing coherence in long-term conversations. However, implementing memory in LLMs is a trade-off between efficiency and depth. Storing too much information increases computational costs and latency. Techniques like retrieval-augmented generation attempt to address this challenge by dynamically accessing relevant external knowledge rather than relying solely on fixed parameter-based storage. Nevertheless, challenges such as memory retrieval accuracy, scalability, and the risk of reinforcing biases persist. While most LLMs focus on text, the next generation will be multimodal, processing and understanding text, images, audio, and video in a unified framework. This shift enables AI to interpret the world in a more human-like manner, improving interaction across different input types. Multimodal training requires specialized architectures, such as transformer-based fusion models, that process multiple data sources simultaneously. Systems like GPT-4V and Flamingo demonstrate early efforts in this direction. They use cross-attention layers and contrastive learning to align textual and visual representations effectively. Applications of multimodal AI include enhanced accessibility tools, creative AI-generated content, and improved human-computer interactions. However, training these models presents challenges, including dataset alignment, computational complexity, and ensuring coherence between different modalities. AI personalization is a key trend, allowing models to adapt responses based on individual user behavior and preferences. Future LLMs will incorporate more dynamic adaptation, improving relevance and engagement. Personalization can be achieved through fine-tuning on user-specific data or real-time adaptation via retrieval-based techniques. While fine-tuning enhances performance, it risks overfitting, making models too specialized. On-the-fly adaptation, such as context-aware prompting, offers a more flexible alternative. Transformers have revolutionized LLM architectures by enabling the effective modeling of long-range dependencies, but as the demand for more sophisticated AI increases, the evolution of these models continues. We're seeing new variations of transformers, such as sparse transformers and models with memory-augmented architectures that extend beyond simple sequence processing. There's also an ongoing exploration of hybrid models, combining transformers with other neural network types for better efficiency and task-specific results. Scaling up LLMs requires innovation in how we handle model weights, parameters, and training mechanisms. Multimodal models that incorporate text, images, and even video are on the rise. These models hold the potential to push LLM capabilities beyond text generation into more holistic, multi-sensory comprehension. Pre-training LLMs on large datasets remains the primary method, but future improvements are focusing on data efficiency. Transfer learning will be taken further, enabling models to adapt quickly to new domains with minimal data and fine-tuning. This minimizes the need for extensive training cycles. Self-supervised learning will continue to expand, allowing models to learn patterns and representations from unannotated data. This approach reduces dependency on labeled datasets, making LLMs more adaptable to diverse real-world challenges. Improved fine-tuning methods will allow for more effective task-specific optimizations without requiring full retraining from scratch. The massive computational costs of training large LLMs have raised concerns about their sustainability and environmental impact. A major area of future LLM development is optimizing training methods for energy efficiency. This includes innovations in hardware, such as GPUs and specialized processors tailored for AI workloads. Another exciting area of improvement is model pruning, where redundant parameters and neurons are systematically removed to make models more efficient while maintaining performance. Sparse models, which only activate a small subset of parameters at any given time, are also becoming increasingly popular for reducing computational load. These advances are critical as AI models become more widespread across industries. While training large LLMs is computationally expensive, the deployment of these models for inference often presents its own set of challenges. As LLMs scale, their size becomes a bottleneck for real-time performance. Efficient inference is necessary for applications that require fast, interactive responses, such as chatbots and real-time decision systems. Reducing latency without compromising the quality of predictions will be a key focus in the coming years. Compression techniques, such as model quantization and pruning, can significantly reduce inference time and memory usage. Additionally, hardware accelerators, e.g., TPUs, specialized ASICs, will continue to play a vital role in speeding up inference for LLMs. The future of fine-tuning LLMs involves more nuanced and adaptive methods. Meta-learning, or learning to learn, will allow models to quickly adapt to new tasks based on a few examples. This could make it possible for LLMs to learn new domains with minimal labeled data. Multitask learning will become more prevalent, where LLMs are trained to solve multiple tasks simultaneously, leading to more flexible and versatile models. Fine-tuning will also shift toward domain-adaptive techniques, where models are better customized for specific industries or problem spaces without requiring large task-specific datasets. Few-shot and zero-shot learning techniques will further push the boundaries of LLM adaptability. The integration of text, images, and other data types into a unified multimodal model represents one of the most exciting areas in LLM development. Multimodal LLMs aim to understand and generate content not only from text, but also from images, videos, and possibly other sensory data. This would make AI systems capable of handling diverse tasks, such as describing images, generating captions for video, or even performing tasks that require contextual understanding across modalities. The challenges include the need for efficient architectures that can handle the complexity of multimodal data while maintaining scalability. Cross-modal knowledge transfer allows models to leverage information from one domain to improve performance in another, resulting in more flexible and generalized learning. Efficient training methods will be critical, as combining modalities requires managing much larger datasets and computational resources. Unsupervised and self-supervised learning are crucial for LLMs to understand vast amounts of unannotated data. These approaches enable models to learn useful representations without relying on explicitly labeled datasets. Unsupervised models have the potential to extract valuable insights from massive datasets without the cost of manual annotation. Self-supervised learning techniques, in particular, have proven to be highly effective in LLMs. These models learn to predict part of the input data from other parts, such as predicting masked words or sentence completion. The future will see improvements in these methods, allowing LLMs to learn even more robust representations with minimal supervision. Challenges include designing better tasks for self-supervised learning and reducing the dependency on massive training corpora. As LLMs are increasingly deployed in critical domains, understanding how they make decisions is essential for trust and accountability. Interpretability will continue to be a major focus, enabling users to gain insights into how LLMs arrive at their predictions or responses. This will allow us to better understand the reasons behind model outputs, which is important for debugging, improving, and ensuring fairness. Future efforts will focus on developing methods to visualize or explain the internal workings of these models. Techniques such as attention visualization, saliency maps, and layer-wise relevance propagation will allow practitioners to gain a clearer understanding of decision-making processes. Increased transparency will help make LLMs more reliable, particularly in areas where decision justification is critical. The energy consumption of training large LLMs is a growing concern, and in the coming years, the AI research community will focus on mitigating the environmental impact of these models. Sustainable AI practices will seek to reduce the carbon footprint of training and deploying large models. Researchers will focus on developing more energy-efficient algorithms and optimizing training procedures to minimize resource usage without sacrificing performance. Energy-aware training techniques can ensure that resources like GPUs and cloud services are used efficiently during model training. Additionally, hardware solutions tailored to AI, such as specialized accelerators or quantum computing, will be explored to significantly reduce the energy demands of large-scale LLMs. The AI community will need to balance model complexity with sustainability as we look toward the future. Transfer learning has been a game changer for LLMs, allowing models pre-trained on large, generic datasets to be fine-tuned on domain-specific tasks with minimal data. This ability to transfer knowledge across tasks is particularly important as it reduces the computational cost of training models from scratch. The future of LLMs lies in enhancing cross-domain transfer learning, allowing models to adapt to a variety of new domains without needing large amounts of task-specific data. However, one of the challenges faced by transfer learning models is domain shift, where the model performs poorly when the source and target domains are very different. Future efforts will focus on domain adaptation techniques, such as domain-specific pre-training or specialized fine-tuning methods, to help mitigate this issue and improve performance across a wider range of applications. Zero-shot learning is a paradigm where an LLM can make predictions on tasks it has never seen during training, relying on the model's ability to generalize and leverage knowledge from similar tasks. In contrast, few-shot learning involves models that can adapt to new tasks with only a few examples. The future will see significant progress in these areas as LLMs become more capable of handling novel tasks with little to no additional training. This will require improved techniques for representing tasks and knowledge transfer from pre-trained models. For example, zero-shot learning in LLMs could be enhanced by developing more sophisticated prompt engineering strategies, where users specify the nature of the task in a way that guides the model's reasoning. However, achieving effective zero-shot and few-shot learning remains a challenge, as these models often struggle with domain-specific nuances that differ from the pre-training environment. As LLMs become more integrated into society, addressing ethical considerations will be critical. One of the primary concerns is the potential for biases in the training data. These biases can be inadvertently learned and perpetuated by the model, resulting in outputs that reflect societal inequalities or stereotypes. Future LLMs will require more sophisticated methods to detect and mitigate these biases during training and fine-tuning processes. Additionally, ensuring fairness and ethical decision-making in generated outputs will be a central focus. Techniques like fairness constraints, adversarial training, and ethical considerations in model evaluation will be explored to make sure that AI does not perpetuate harmful or discriminatory patterns. The aim is to develop models that can generate outputs that are not only technically accurate, but also ethically sound. LLMs are susceptible to adversarial attacks, where small manipulations to input data can lead to incorrect predictions. As LLMs become more widely deployed, ensuring their robustness against such attacks will be crucial. Researchers are already developing methods to harden models, making them less susceptible to adversarial perturbations. Techniques such as adversarial training, where the model is exposed to adversarial examples during training, will become standard practice to increase robustness. Additionally, evaluating model performance in the presence of adversarial attacks will help ensure that LLMs maintain reliability in real-world scenarios. However, striking a balance between robustness and performance remains a challenge, as defensive techniques can sometimes reduce the overall efficiency or accuracy of the model. The future of LLM development will require collaboration across disciplines, bringing together AI researchers with experts from linguistics, cognitive science, and domain-specific fields. This interdisciplinary approach will allow for the incorporation of deeper insights into language processing and understanding, enabling LLMs to better capture the complexities of human language. Bridging the gap between AI and other disciplines, such as understanding the cognitive mechanisms behind language and learning, will improve the naturalness and applicability of LLMs. Additionally, diverse research teams from various backgrounds will help reduce biases and ensure that the models reflect a wider array of perspectives and experiences. This cross-disciplinary exchange of knowledge will be essential in overcoming the challenges that lie ahead. Quantum computing has the potential to revolutionize LLM training by providing significant computational speedups over classical computing methods. Quantum algorithms can potentially solve certain problems much more efficiently, allowing for faster and more scalable model training. For example, quantum computing could be used to accelerate optimization processes, enhance the exploration of hyperparameter spaces, or improve data sampling techniques. However, there are several challenges to overcome before quantum computing can be practically integrated into LLM development. Current quantum hardware is still in its infancy, and scalable quantum machines with the necessary computational power are not yet available. Additionally, new quantum algorithms need to be developed that are specifically tailored to AI tasks. Nonetheless, quantum machine learning could be a game changer for LLMs in the long term. The future of LLMs will likely see an increase in their ability to process and generate multimodal data. Currently, most LLMs primarily focus on textual input, but integrating other data types such as images, audio, and even video can allow models to understand and generate more complex responses. By combining modalities, LLMs can process richer context and provide more nuanced outputs. For instance, multimodal models can combine visual data with textual information to answer questions about images or videos. This integration also extends to more natural human-AI interactions, where models could analyze audio inputs, understand body language through images, and respond contextually with text. However, aligning and synchronizing multiple modalities is a challenging task, and ensuring these models maintain consistency in reasoning and output is crucial for their effective use. One of the promising directions for the future of LLMs is the ability to engage in continuous learning. Traditional models typically require retraining on large datasets to adapt to new information, but continuous learning allows models to update themselves incrementally over time, learning from new data without forgetting what they have previously learned, a phenomenon known as catastrophic forgetting. This ability would allow LLMs to remain relevant and improve over time, adapting to new language trends, societal changes, and emerging topics without extensive retraining. Implementing incremental learning strategies, such as rehearsal methods or memory networks, is key to achieving this. The main challenge, however, lies in designing systems that can integrate new knowledge efficiently and effectively while preventing the introduction of inconsistencies or errors in existing knowledge. As LLMs become more integrated into critical applications, the need for explainability and interpretability in their decision-making processes grows. Being able to explain why a model made a particular decision is crucial for building trust with users and for debugging the system. In complex systems like LLMs, this can be particularly difficult due to the vast number of parameters involved and the often opaque nature of deep learning models. Future LLMs will incorporate techniques like attention mechanisms, saliency mapping, and layer-wise relevance propagation, which can help trace the decision-making process of the model. These approaches can provide insights into which parts of the input data were most influential in shaping the model's output. Ensuring interpretability in large models without sacrificing performance remains a technical challenge, but it is a crucial area for the development of responsible AI. As LLMs grow in size and complexity, their environmental and financial costs are becoming a significant concern. The training of large models consumes vast amounts of energy, leading to high carbon emissions and making AI development less sustainable. In the future, innovations will focus on improving model efficiency to reduce these costs. One avenue of research is optimizing training algorithms to be more efficient, requiring fewer computations and less energy while maintaining high performance. Additionally, energy-efficient hardware, such as specialized AI accelerators and quantum computing, could play a role in making large-scale training more sustainable. Implementing best practices for sustainable AI, such as using renewable energy sources for data centers, will be essential in mitigating the environmental impact of AI. The field of LLMs is advancing rapidly, and with these advancements comes the need for new and more accurate methods for evaluating model performance. Traditional benchmarks, which focus on accuracy and computational efficiency, need to be expanded to include more comprehensive criteria that reflect how well models perform in real-world applications. In the future, we'll see the development of evaluation metrics that go beyond standard tasks like language generation or question answering, incorporating aspects such as model robustness, long-term generalization, and adaptability. Quantitative measures will still be important, but qualitative evaluations of model behavior in complex, dynamic environments will also be essential for assessing the true capabilities of LLMs. This dual approach to evaluation will be key to understanding model performance in the wild. In the context of large language models, LLMs, optimization algorithms like gradient descent are critical to training. The Atom optimizer, one of the most commonly used, adapts the learning rate based on the momentums of the gradients, making it efficient for training deep neural networks. However, as LLMs grow larger, the optimization process faces challenges like vanishing/exploding gradients and slow convergence. Future improvements in optimization algorithms might include adaptive methods that better handle the massive scale of data and parameters in LLMs. For instance, methods like LAM, layer-wise adaptive moments, or newer variants of Atom could improve convergence speed and robustness. Researchers are also working on algorithms that address the trade-off between precision and efficiency, making them more suitable for massive models. Effective optimization will be crucial for scaling LLMs and reducing the computational costs associated with training. Integrating structured external knowledge into LLMs can significantly enhance their performance, especially in tasks requiring domain expertise. While LLMs excel in understanding and generating language, they often lack detailed, structured knowledge. Techniques like incorporating knowledge graphs or external databases can help. Knowledge graphs represent relationships between entities in a formal structure, providing a rich context for model training. By integrating knowledge graphs, LLMs can learn to reason more effectively, combining their learned patterns with factual, structured knowledge. However, challenges persist, such as ensuring that the knowledge is dynamically updated and correctly aligned with the model's learning. The future of LLMs could see the seamless integration of various external knowledge sources, enhancing accuracy and reasoning ability. Model adaptation refers to the process of fine-tuning or retraining a pre-existing large language model, LLM, to perform well in a specific domain, such as legal, medical, or technical fields. While LLMs like GPT models are trained on broad data, fine-tuning allows them to specialize in narrower contexts, improving accuracy and relevance. Fine-tuning involves retraining the model on a domain-specific dataset to refine the knowledge and behaviors of the model, adapting it to new terminology, jargon, and domain-specific logic. Zero-shot learning, where a model performs tasks without explicit training on a given domain, and transfer learning, where knowledge from one domain helps improve performance in another, are also vital strategies for model adaptation. However, challenges include ensuring that the adapted model doesn't overfit to a specific domain and can still perform well across other, more general tasks. Additionally, maintaining the model's ability to generalize while adapting it to specialized knowledge remains a significant area of ongoing research. Future advancements will likely focus on creating more efficient and dynamic adaptation strategies that require minimal retraining data. Training large-scale LLMs requires vast computational resources, which leads to high costs and environmental concerns. Researchers are focused on developing methods to make the training process more efficient while preserving model performance. Techniques such as memory-efficient training aim to reduce the memory footprint by optimizing the way data is processed and stored during training. Additionally, methods like knowledge distillation, compressing a large model into a smaller one, and pruning, removing unnecessary neurons or weights, help reduce the size and computational load of LLMs. In the future, the combination of these methods with more efficient hardware, like specialized chips, could make training even more scalable, enabling the creation of more powerful models without overwhelming resource requirements. As LLMs become more powerful, understanding how they make decisions becomes increasingly important. Interpretability refers to the ability to understand and explain how a model reaches a particular output. For LLMs, this could involve techniques like attention visualization, which helps track how different parts of input text influence the model's output. Techniques for explainable AI, XAI, aim to provide insights into model behavior, enabling more trust in complex models. This is crucial in applications where decisions need to be transparent, such as healthcare or finance. As LLMs evolve, the integration of more advanced interpretability methods will allow developers and users to better understand model behavior, leading to more reliable and ethical AI systems. The future of AI will likely include increasing efforts toward explainable models, balancing performance with transparency. This concludes the final day of our AI crash course. Congratulations! We've covered many different topics in a short time and hope you've learned something and liked the course. For more AI courses and interview materials, please go to our website at bauzier.com.